Hello students, in this video we are going to understand and solve this problem which is in front of you. I will just read out the problem first. Two thin circular discs of mass m and 4m. So these are the two discs. One is small disc mass m and big disc is mass 4m. Having radii of a and 2a. This is a, this is 2a. Respectively, are rigidly fixed by a massless rigid rod of length L equal to square root of 24a. So this is that rigid rod which connects the center of the two discs, and this is massless and it's of length square root of 24a. This assembly is laid on a firm and flat surface. So this is the flat surface and set rolling without slipping on the surface so that the angular speed of the axis of the rod is omega. So this particular axis is the axis along which these two discs are set rotating. So the rotational speed is omega, and because of this speed they will start moving on this surface. So this is your xy plane. This surface is around xy plane. This is z axis, and so this is set rolling without slipping. So this is, there is no slipping. The angular momentum of the entire assembly about point O is L. Right? So this is the angular momentum is considered as L. Which of the following statements are true? So the first statement is the center of mass of the assembly rotates about z axis at an angular speed of w or omega by 5. The magnitude of angular momentum of the center of mass of the assembly about the point O is 81 ma square omega. The third, the magnitude of angular momentum of the assembly about its center of mass is 17 ma square omega by 2. And lastly, the magnitude of the z component of L bar is 55 ma square omega. So actually this particular problem is actually, there are 4 sub questions they have asked. So instead of just finding out which one is true, my intention is to solve each one of them as a separate sub question, and we'll try to understand that. So in this video I am going to cover the first one. The center of mass of the assembly rotates about z axis with an angular speed of omega by 5. So if you look at this, I am going to look at this first question as find out the angular speed of the rotation of the center of mass of the assembly about z axis. Right, and whether then I will check whether it is given equal to whatever is given value. So to do this we are going to do 4-step approach. First, find out the location of the center of mass of the assembly, because it is talking about the angular speed of rotation of center of mass of the assembly. So first we will identify where it lies, then understand the dynamics of a circular disc which is at right angles to the flat surface along xy plane, rotating on a flat surface along xy plane without slipping. So before going for the tilted one, this tilted one, we will consider that it is perfectly vertical, and then understand the dynamics. And in the third step we will make it tilted by with an angle theta as given in the problem, and then we will understand this dynamics of this circular disc tilted at an angle theta and rotating without slipping on xy plane. And finally we will do the calculation of the required angular speed. Now to understand this, I have kept this assembly onto this xyz sort of our axis, the 3 axis. We are going to, the requirement is to find out the speed of this entire center of mass of this entire assembly along z axis. So it is rotating along z axis. So right now this z axis is here. So if you put the z axis here, then it will look like this. But I have just, for our understanding, I have kept it here. So this is the assembly, big and this small disk, and this is the rod. So somewhere on this rod the center of mass will lie. So in the first thing we will try to calculate this center of mass. Then they are asking us what is the angular speed with which the center of mass is rotating around this z axis. So this is our z plane, so this is z axis, and we will try to calculate that, because when this assembly starts rotating, this omega speed will make it revolve around this z axis, and that rotational speed is what they are asking us to do. Now let us go step by step. First we will understand where is this center of mass is exactly located. So to calculate that, let us understand this. In a these two disks are there, given disk, and this is the center of mass. Let the center of mass be away from the smaller disk center with x of center of mass, and the length between the two centers is L. So if you consider this small axis, the small disk, as a point mass m along at A, and this big axis, this disk as also a point mass 4m at B, then this entire assembly will be reduced to this. This rod has no weight, so it will not get into the calculation of center of mass. So we have two masses, one is m here, another is 4m here. So by using the weighted average formula, by considering this as the point around which we will calculate, so the formula will go like this. The x com, right, into m plus 4m, because m plus 4m into x com is equal to m into 0 plus 4m into L. So the center of mass is given by, when you divide this by m plus 4m, and when you resolve this you will get it is 4 by 5 times L. So actually the center of mass lies at 4 by 5 times L. So somewhere, actually this diagram is showing almost halfway, but it will be somewhere here, because it will be nearer to the heavier, or have the mass, the higher mass disk. So 4 by 5 times this, somewhere here it will come. So this is our center of mass location we have identified. Now when we have a disk which is kept at right angles to the surface, and it is set rotating with an angle, with a angular speed of omega, then it will rotate and it will travel in a straight line, and in one rotation of this it will, the circumference is 2 pi, so it will cover a distance of 2 pi a. So this point will again come into touch with the surface here after 2 pi a. So this is how the calculation is to be done. Now we will again go back to our problem, where in our case these discs are not right angle, they are tilted with the angle say theta. So when we start rotating this, actually this particular point or this particular disk will revolve around z axis. It will not go in a straight line, because it is tilted at an angle, and because of that it will rotate in a circular way. And this particular rotation speed is, we assume to be omega dash. So omega dash is what we want to find out. But before we go there, we need to find out the this particular center of mass is rotating also at omega. Now as we know that this particular, before going there, the center of mass will rotate at the same angular speed with any other point on this assembly. All will be rotating in this along the z axis, uh, at different xy planes. So this point C is rotating in this xy plane. This center of mass will be rotating in a higher xy plane, but all will be rotating with the same angular speed. And to find out the angular speed of center of mass, we can as well find out the angular speed of this point of contact of the slowest of the smaller disk. So if we say C, the point C's rotational speed will be the same as the rotational speed of the center of mass. So before we calculate that, we will actually require to find out the radius of this particular path, this particular path of this small radius. So let us take this as R1, and this is L, and this is a right angle at A. So this triangle will look like this. This is L, this is A, this is the radius of the the disk, and this is R1, which is going to be the radius of the path of circular path which is going to be followed. So by using Pythagoras, we will get R1 square equal to L square plus A square, and L they have given us as 20 square root of 24A. So when you square it, it will be 24A square. So this will be 25A square, and R1 will be 5A. So we have calculated 5A as R1. Now with the one rotation of this disk at omega, uh, and this particular rotation will be at omega 1. So when you have one particular rotation, complete rotation of a small disk, it will cover this arc, which is C dash, which will be equal to the circumference of the small disk, which is 2 pi. Now both are happening in the same time frame, because the time it will take for this small disk to rotate in one rotation, the same time it will require this particular point C to again come back or traverse the arc C dash. So if this angle is theta 1, we will do the calculation as one rotation of smaller disk at omega, it will be 2 pi by t. So if it is taking time t, it will be 2 pi by t. So t is equal to 2 pi by omega. This is my first equation. And for the arc CC dash covered, it is also covered in the same time interval. So W or omega 1 equal to theta 1 upon t. So theta 1, this theta 1 upon time t, and then theta 1 is nothing but, so how you calculate theta 1? 2 pi a, the arc, upon the radius, because radius into theta 1 is 2 pi a, right? So we will get 2 pi a upon r1 upon t. So t will be 2 pi a upon r1 omega 1, and when we equate this t and this t, the right sides we equate, and you will get omega 1 equal to 1 by 5 times omega. So the first statement actually is true, but we wanted to just not to find out whether the statement is true. We wanted to arrive at this angular speed, and which we have done. So in my second video, we will try to solve this second point or second statement wala question. Thank you. If you are liking this series and if you want to learn more, you can always subscribe to this channel as well as hit the bell icon. Thank you.